Morning, everyone. Very well, nice welcome to this workshop session today. So I'm Johannes from Certora. So I'm really happy to walk you through today. We're gonna have an interactive session, like a little workshop on how to formally verify your Soroban contracts. So we are really excited to announce we have a new release of a formal verification tool that you can use to verify your Soroban contracts, and we're gonna walk you through setup Cetora's tool and verify on a small example how we show you how you can formally verify a Soroban contract. So this is actually a really exciting project that our team has been working on over the last year, and so mostly I want to go through who has been working on it. It's really like a big team that has been working on it, especially like Chandra in the US, Alex and Eric have been really pushing hard to really transforming a tool that we already have been working on over the last years on Solidity to also port it to Stellar. And so, like, really the last days we released the first beta version of it that we're gonna demonstrate today, and you can try it out yourself today. So I see some of you brought your laptops, so I hope we can set you up the tool, walk you through, and show how you can really formally verify your contracts. I'll first, in this workshop, I'm gonna first give a 10 minutes really short introduction what formal verification is from a development perspective, what does it help you, which guarantees does it provide you, and then we really start the setup, so you have the opportunity to set up and install Certora Sunbeam yourself, and then you can run your first small tests and write your specifications. At the end of the workshop, we also then talk about how can you have even more guarantees that the specifications you write are more are correct, that you have more certainty about your specifications. But that's something we'll cover over the workshop. So yeah, as I said, the agenda will be roughly short intro to formal verification. Then you'll have time, 10, 15, maybe 20 minutes to set up the tool yourself. So be prepared, have your laptop ready, and then we start writing properties for a Soroban contract. I'll also show you in the first part how the output looks like, and then we speak about mutation testing. So first of all, who has used formal verification before? I see a few hands. Great. So it doesn't matter, we'll show you and demonstrate what it actually is from a developer perspective. So think about the following. Think about you have an ERC token contract that you implemented yourself, and what do you normally do to verify or test that you kind of are sure the implementation is correct? You will start writing unit tests for sure. So here I have a little example of a basic unit test that we want to test this function, the transfer function of an ERC20 token. So an ERC20 function, the transfer takes an input, an address, a from address, and a to address, and an amount that you want to transfer. So it's really like a transfer of the balance from one contract to the other. So what will you have to write this test? What will you do is you think about the balances before and after this, before and after you call this method. So you think about the balance of the from address, think about the balance of the to address, and exactly before and after execution of this contract method. Then what will you do at a unit test level? What you then do is normally you set up your environment, you set up your inputs to fixed inputs. You think about some inputs that you want to test on, you specify them explicitly. For instance, you create a fixed address that you want to transfer the amount of to, and you create a fixed from address that you will transfer the amount to. So, and then at the end you will add an assert saying, okay, this is what I want to assert. For the transfer function, I want to say the balance to increases by exactly amount, versus the balance from clearly reduces exactly by amount. Well, that's all good to have and it's really important to write. At the same time, you really must think of what did you actually do? You really fixed certain inputs here and then test that it's working exactly for this input. And this is actually where formal verification has a really different mindset. You have to think of it differently what really formal verification does. On this specific test example, you basically, when you write a formal verification test, and this is what I present here, is like you do the same thing, but you really test it on all inputs at the same time. You say you have this to and the from address, you have the amount, and you really, what you actually want to say is that as long as the to address is not the same as the from address, so as long as they are different, and the addresses actually exist, you want to say that this property holds. So you have like the require. This is a precondition that you set basically, and if this precondition holds, this postcondition is also true. So instead of fixing certain inputs, you really now execute this code part and verify it over all contracts. So you see, it's like this is actually like a concrete example of a specification you can write today in this workshop. But you'll see it's really like you can write this in Rust and really like a regular test, but then we'll execute it using Cetora as a formal verification test. So it really, from a developer perspective, and that's what we aim here for as well, is to keep it as close as possible to your regular development lifecycle. It's just writing a different form of test here. And again, you get more certainties because you get, instead of fixing to, from, and amount here, you will cover the entire search space for the inputs. And that's what we really want to do because you really want to test for these corner cases that you normally miss. I brought a second example, and this is an example actually taken from the documentation of Stella as well, and to show you also like where this may break. So in this example, you have an increment contract that really just has a storage information about a counter, and in the storage information, you really, whenever you call the function increment, you increase this counter. So you see here, you set up the environment, you register this contract, and then on the client, on the contract, you actually call this function increment. In this test case, if you call it once, the output is 1. If you call it twice, the output is 2. And if you call it the third time, it will just be 3. So as you see here in this example, you kind of, with this test case, you kind of enumerate what you actually expect. So you may think of writing a for loop that would then execute it like for every counter and see what happens. Technically, you could do it. But if what you actually want to verify here is, or prove, that whenever you call increment, you want to say, hey, the current counter was incremented by 1. So this is how you would write this as a formal verification test. So with increment contract current, you basically get the current counter, current value, which I call previous here. Then you increment this counter by 1, and you'll see that at the end, you can assert that the next value is equal to previous plus 1. And this is actually what you want to verify over this contract here, instead of explicitly enumerating all states that you have. So this is something that I want to... There was a question? Go ahead. Yes. So excellent question, because actually I'm just going to show you how this will all look like when you actually execute this on Cetora. So I have like here a little example run how this would look like in Cetora. So, and you'll be able to do this afterwards yourself. So this is the user interface of Cetora. So you can, in your command line, in your, say, Visual Studio Code, you can execute this specification, this test, and then it will submit the job to Cetora and run our verification tool over it. What you'll see here is the output. You see here, first of all, let me start with the files. You see we have a folder source code folder which contains the actual contract that we're going to verify. Then you see a Certora folder which contains the specifications, and this is exactly like what I just showed on the slides. So you see here's the implementation of this little of this rule that you write. So you have a current. It's exactly the demo I had on the slides, and you also see the test case here. So this is what we verified here, and over here in this tab, the rules tab, you actually see we executed this formal verification function. It's annotated with a macro rule here that it knows. That's how Cetora knows how to pick up which tests or which rules to verify. And so you see the output here. So now it's interesting because this specification that we wrote actually fails. And now we want to understand why did it fail. And so I'm gonna go over these details, what happens on the background just now, but for now, it's sufficient to understand if you have a violated, you will actually get a call trace, meaning you get a execution path through your program where this and how this property was violated. So you see here on the right, this is our call trace, and you can see that this actually matches the function verification test. You see here it calls the function current, which gave you the current value of that counter. You see there is a function called to increment here, which then will increment the given counter, and then at the end you have this assert and that you verified. So now we have a failure here. So we see that we have some print statements here where this is how you can print out the current values. So here we see a counter example of this property, and we see the current values. So if the counter has this value, it's a hex value 854. Sorry, I don't want to transform the decimal right now. But if the value is 854 in hex, you'll see that the next value also will stay the same value. This is suspicious, and you wonder why didn't the counter increase? And so, if you then look at the implementation, actually, you'll see that there is. Here's the function increment. You'll see it get some storage, the value from the instance storage, and then there is here an interesting if condition. Only if the counter is smaller than some given maximal counter, this property holds. Otherwise, the counter won't be increased. So this is actually like, and if you look at the implementation, you see that, oh, interesting, so the max counter is only on 100. There is kind of like an assumption on this increment function that it only goes up to 100 for whatever reason. What I want to demonstrate here is that using formal verification, you are actually able to understand the control flow of a function. So it gives you a counter example where you actually condition that you think should hold doesn't hold anymore. So if you this counter example now says if this counter was at some point at this value, it won't increase anymore. So back to the presentation. So what he could do to get this verified, I mean, you have to think about now if this increment function is correctly implemented, and if you want to get it verified, it could be that this max counter should be, for whatever reason, 100. It should hopefully be documented if that's the case. So you can see what you need to do is basically say, well, you can change the specification if that's the correct thing to do. You can say, okay, I require that the pref count is actually smaller than 100, this max counter that I had, and then this test succeeds. Really depends on what you want to verify, if that property holds, and so on. But now you can prove this property. And the interesting part here is that you kind of make these assumptions that you have in your code actually visible in your specification, because you need to specify all these requirements. You have a lot of assumptions normally that are not documented, and this is where formal verification really helps you to get these assumptions out of your implementation and think about the right assumptions. So it really looks like for these extreme extreme corner cases that actually need to be covered and need to be handled because it could be a bug. Well, so this is really what I wanted to show and demonstrate how this works. Before I show you how this actually, how you can do it, how you can run the tool yourself and how to execute this tool, I want to just give another high-level information overview of what we're actually doing here. So we have, when you want to run Cetora, you normally have your code that you actually want to verify, and somewhere else you have your specifications. So typically in this Cetora specs folder, you will have these specifications in which you implement these rules, use the require and use the CVT assert to kind of explicitly write your conditions, your pre and post conditions. Then you execute the Certora tool, and this will actually internally transform your test into mathematical formulas, and then use SMT solving to actually see, can I verify this property that I have, or do I get a counter example? I'll do that just now. So at the end, you'll basically either get a proof saying your property was verified, so the condition holds, or you get a counter example, and this counter example will tell you there is some bug, some condition that you haven't thought of, and you can think about this counter example, see if you need to either change your code or your specification. There are also cases in which the tool runs into timeouts where it just doesn't know the actual answer, because an SMT solver that we use under the hood basically doesn't know the answer. And we run into a timeout, and we just don't know. We don't want to give information. If we don't know, we just don't want to give incorrect information, because we really want to formally verify the contract. So this sometimes happens. We are working a lot on how to resolve these timeouts. That's how it is. Yeah, so I want to go in this slide just briefly over the infrastructure to understand more what we're actually doing, what's happening under the hood. So you'll, as input, as I said, you have this code in Rust and the specification. Also in Rust, we'll then compile your code with Cargo or the Rust compiler to WebAssembly. And then we actually use the WebAssembly that you also deploy on the blockchain. We decompile it to an intermediate representation, to our own language that basically we call it TAC, the 3-address code. And this one we then transform into mathematical formulas. And an SMT solver is able to understand and reason about these mathematical formulas and can either say these formulas are satisfiable or not satisfiable. If they are satisfiable, it means that I can have a counter example back in, if I translate it back to my code, I can have a counter example that shows these formulas aren't able to be verified, and so I know that there is some kind of information or a bug in my code. If the SMT solver is able to verify that this formula holds, then I know the actual specification is also correct. Well, yeah, so this is the entire pipeline. So after the SMT solving, we either decide, okay, is it a bug, is it a verified, and then we report all this back. So we go back in the pipeline, transform the formulas back to TACT, and then back to Rust language level to show and present the information in the web report. Right, are there any questions at this point? Yes, that's an excellent question. Actually, we do it also for some formulas, like accessing storage, for instance, because you see, like these formulas will just explode if you really put all this code into. So we model the SDK here. Yeah. Okay. All right. So this is the point where it's actually up to you now to get ready and start. You can sign up on the website. We have a little Git repository with a tutorial, with a contract, with a small test, with a small specification that you can write yourself. And so I want to briefly show you what this is. I'll put the slide on just now again, so you can follow the link to the Yes, we have the. Yes, we are absolutely there to help. Sure. All right, so we prepared like a small workshop tutorial here. This is the Git repository that you can check out, and there are instructions on how to set up the tool, how to install Certora Sunbeam. Then you see what prerequisite do we have, like install Stellar CLI and so on. And then further down you find exercises that you can work through. So there's a little warm-up session, and then more exercises in which you have to write specifications for that existing contract. So I really encourage you now to check out this repository and then start installing the brewer. And we, as well, my colleague Alex is here to help assisting get the setup correct and get you going. Right, so feel free to ask us for questions. One thing that I wanted to show is also the content of this repository. So if you check out this repository, yes?
We don't have a lot of people with laptops, so maybe if people can like start installing the background, and if you can like skip to the slides that explain like how to formally verify Soroban contracts.
Excellent, excellent. So give me like a moment to so whoever is interested, you can scan this QR code, and then this will redirect you to this GitHub repository, which you can check out. There are the instructions. You can start working on this. I'll fast forward to the actual exercise 1 to see how this actually looks like. So this is a short demo. So if you check out this repository, you'll actually see a Cetora folder, a source folder. You have a lib folder, and in this lib folder, you see an ERC20 token that we implemented. It has transfer function, it has a mint function, it has a burn function, and a balance function. So you see, this is like a minimal example that you can use here. And then you also see the Cetora folder. In the Cetora folder, we ignore the mutants for now. You'll see the specifications that you can write, and you see here there is a rule that you can write, and this is for exercise 0. So this is a given rule that you can just execute. And what you can do is on this folder, if you execute this rule, you can just run Cetora run, and then config setup. This is the first example you can run. Hit enter, and internally it's now building actually this project, including the test and the specifications and your actual contract, and it will then give you a link to the verification result. So you'll then see actually the web UI that I just showed you, in which it will execute this entire process of transforming it into SMT and then trying to verify or find a violation of your property. It will take a couple of minutes until this job is done, but you'll see that right now. So we also, on this repository, have a solutions branch, in which you're able to also find the solutions of these specifications. If you're curious, so you can check that out later. So let's see. So the verification here is still in progress. We'll take a moment. I'll show you actually the final status of this job that I just submitted. So it will, in this say, is able to verify the property that you had, and it's able to. In exercise 1, you actually need to. The specification actually uses what's called a satisfy. A satisfy, instead of an assert, tries to reason: is this point? Do I find an example that reaches this code point in my execution? So in this case, it's a really minimal example using balance here, and then you execute balance and want to understand, is this code actually reachable? So this is like a really minimal example. It's really just a reachability check that we do here, saying, okay, are there any inputs that this point can be reached? And what you see here, then you also see a call trace that then tells you, okay, this is how this code location can be actually reached. The satisfy is an interesting way of, if you need to debug some code, sometimes you need to find places in your code and the preconditions that actually led to this place in the code. If you do that manually, you need to think of all the preconditions that you actually have to reach that code. You can use a satisfy, place it in the code you want to reach, then run formal verification, and will actually show you the inputs that are required to reach that code in the location. Right, so yeah, are there actually currently any questions? So this is like exercise 0 where you run the sanity. There are more exercises. Are there any questions right now? So I see some of you are setting up the code. All right, so one thing that I want to then demonstrate quickly as well is, assume you have reached your specification, you've written your specification. There's always the challenge of, what did I actually test for? How good are my specifications? And so what I want to do is then also really test my specification. What you can do there is start injecting bugs into your program and start mutating your actual implementation to inject bugs and then find violations. So there's also in the repository, you see there are also some mutants that we prepared, and you see that you can really like write your specifications and then start injecting bugs into your actual library, into your code, and then execute formal verification and see how good your specifications are. So this is something we also recommend you. You write your specifications, but then also write mutants to actually understand how well my specifications are. So I'll go back to the repository because we also have some examples there. So I'll fast forward now to exercise 4. You can feel free to set up this at home. It's free of use, so feel free to use this setup. Go through this repository at home and at your own time, and then really set up this prover. So what I want to show is like the final version of exercise 4. So if you went down all the way of specifying all your properties, for this example, in this workshop, you're actually able to write a couple of properties. I'll show you what you can write here. So for exercise 1, what you actually need to show is that if you have a new token, then the balance of this new address will actually be 0. So if you mint a new token, the balance will be for sure 0. This is the property you can write in exercise 1. Exercise 2 is about what I showed in this first example on the presentation. So you can show that transfer is correct. So you'll see that balance 2 will be increased by amount after transfer, and balance from will be reduced by amount.
On this one, how I would imagine a transfer there is probably an overflow condition in there. Sorry. There is probably an overflow condition in the transfer function if it's just doing a straight addition. I mean, I don't know the implementation, but like if there is nothing special, it should just crash in Rust, right? Like you get a overflow. So like, how is that represented in the contract? I mean, in the.
It's actually an excellent question. Let's quickly look at this. So you see in the contract, you'll have this transfer function, and it will spend balance. And this is something like exactly what we are still. So you see that there should be here. Thinking about it right now. Give me a second.
And basically, I think I would expect to see some sort of reachability condition that says, oh, if you're, if the amount minor, I mean, whatever, like there's some formula, right? And then you end up with the overflow condition.
Yes, yes.
Both on the plus and the minus.
So we currently, this is exactly where we kind of like, still working on this is work in progress right now. We kind of like you have to think SMT solver will actually model this at a math int, so an actual mathematical integer, versus here is it's an assigned integer right now. So you have to these are the conditions that we're still currently modeling to actually exactly find these traces right now.
Okay.
Yeah, exactly. That's exactly these cases that you need to think of that are right. Good. So something else that you should, back to the exercises on exercise 2, what you also can verify here is that actually if you do a transfer, you ensure that for other addresses that are not participating in this transfer, you are actually, the balance will remain unchanged. So if you look at this property now, you see if you require that 2 and other are not equal, so they are really different, you'll see that if you perform the transfer, balance before and balance after will be different. This is a property you also want to have, that if you transfer on any other address, nothing will change for sure. So let me just think right now to. Right, we wanted to see what happens if if we do mutation testing. Let me find the right link right now. All right, so we've seen if you manage to get to exercise 4, you have all these specifications for your token, and then you want to start injecting bugs to actually see how well your specification is. So in this run, we have a mutant that actually does the following. You see here, it will just execute. So this is the mutant that we wrote. We just copied the line. Instead of a transfer, it will just call spend balance twice instead of spend balance and receive balance function, which should be correct. So if you change this part in the code, you'll see that your actual specification, the transfer is correct, fails. and you see that you'll get a counter example here. So so for exercise 4, again, the verification succeeded. We changed now the lib file, the actual contract, and you see that we changed transfer here to call spend balance twice, and then you see your specification will fail. So this is also an important part of formal verification. So you write your specifications, and then also make sure your specifications are actually correct by injecting bugs. That way you know if this would still verify, you have to think of, did I actually correctly specify my contract? Because otherwise, then you have to think of a new specification that you missed writing. This is how we work currently. Like you write the formal specification, and then as a additional guarantee, we also write mutants, execute these mutants to then cover all these corner cases and ensure that the specification is correct. Because you always will have the issue of how much coverage also do you have with your specification. All right. This actually wraps up the workshop. So I really encourage you now to set up the prover. I leave the slide here, where you check out the Git repository, walk through the exercises. So we're here to, I guess the best thing is for you to right now do the sign up, and then run your first verification using this exercise. Thank you.